Hi, I'm Jesse. I've been a driver developer for MongoDB for almost 5 years now. I remember when I first began working for MongoDB, I'd only been working for them for a few months, and a guy came to office hours in our old office in downtown Manhattan in Soho. And he wanted to ask a question that I didn't have the answer to. I don't remember his name, so I'm going to call him Ian. I do remember his question, and it was, what is a simple, smart strategy for retrying operations that would make my MongoDB application resilient in the face of network errors and step downs? Our little office, it really didn't have any place for me and Ian to meet and talk, so we walked into this little room on the side of the office. It had no windows, it had nasty fluorescent lighting. It didn't even have any chairs, so Ian and I sat right next to each other on a table that was in that room. And his face, he had this tousled hair and these dark circles under his eyes. He looked as if he'd actually been up the whole night before, worrying about this question: how do I make a resilient application? And unfortunately, I didn't really have an answer for him. All I could say was, we can't really formulate a single strategy for dealing with network errors and failovers and everything else that can go wrong because we don't know your application. There's a variety of operations you can do, and there's a variety of trade-offs you might want to make between latency and reliability, between the danger of doing an operation twice versus the danger of not doing it at all. There's no single strategy that is going to work for everybody, and that's why we haven't published any guidance. It would just be too complicated. And besides, all the drivers act differently, and so we would have to publish a different guide for every language, even if we could come up with something that would work for every application. So Ian was not happy about this answer, and neither was I. And in the years since, I've worked to be able to come up with a good answer for Ian. One of the things that I've done is I wrote a spec called the Server Discovery and Monitoring Spec for how all of the drivers should discover the state of the servers they're connected to and how they should deal with network errors and other errors. And once I wrote that and all of the drivers implemented it, it was actually possible to come up with a smart strategy. So that's what I'm going to share with you today. The operation that we're going to try to do resiliently is this one. So this is an update 1, and it updates the document whose ID is today's date, and it's trying to count some sort of event. So it wants to increment a field named counter. And if this is the first time today that this update 1 occurs, then it's going to create the document, so that's what that upsert equals true means. And let's say that there are many threads or many processes that might all be doing this at once, so this needs to be concurrency safe. How do we make this operation resilient? Well, first of all, what can go wrong? If you send an update 1 message to a MongoDB server and there's some sort of network blip, what happens? Well, from the client's perspective, you get some sort of error from the network layer. Maybe it's a TCP reset or a timeout, but unfortunately, we don't know whether the server received the message or not. So we don't know if the counter was incremented. All we know is that we couldn't read the server response. There might also be a failover, in which case we sent the update 1 message to the server that we thought was the primary, and it responds not master. I'm no longer the primary. And in this case, we know for sure that the message was not processed, but we don't know who the new primary is yet. The third kind of error is network down or network outage that might last some time. And when we first detect this problem, it looks exactly like any other network blip. We send a message to the server and we simply can't read the response. But what distinguishes a blip from a more long-lasting outage is that if we keep retrying this operation, we'll keep getting a network error, and retrying is in vain. But we don't know that the first time. And the final kind of error that we're going to look at is a command error, where you send the update1 message to MongoDB and it returns a specific error saying that the command was received, but it could not be executed. Maybe because we're not authorized, or because the operation was misformatted, or the server's out of disk space, or something like that. And again, retrying it won't be helpful here. So given that these four errors, they're not completely distinguishable from each other, and they all require different responses from our application, how can we come up with a single smart strategy that Ian can implement that will make his application resilient? Well, I've seen a lot of bad retry strategies out there, but before we get into that, you might be wondering whether this is specific to MongoDB because we don't have transactions. So consider if we were using a traditional SQL database server, and we open a transaction and we do some operations and send the commit message, and then there's a network blip, and we can't read the confirmation response from the server. Do we know whether that transaction has been committed or not? Doing an operation exactly once with a SQL server has the same problems as it does with a non-transactional server like MongoDB. So it's not about the lack of transactions. So with that out of the way, let's try to formulate a smart strategy for MongoDB. And in order to begin to formulate this strategy, first we need to consider how drivers themselves respond to the four kinds of errors. And then we'll figure out how the application that uses the driver should respond in turn. So if there's a network blip, the driver will set the state of the server it was trying to talk to unknown, and it will throw an exception. What I mean is that if the driver thought that the server was a primary or a secondary, it updates its data structures that internally represent its view of the server, and it will say, I used to know what this server was, but now I don't know, so I'll set the server type to unknown and then throw an exception. The same goes if there's a primary failure. If the driver processes a not master error, it sets the state to unknown, throws an exception, and a network down, a long-term network outage, it looks just like a network blip and the driver responds just the same. And in the case of a command error, nothing about what the driver thinks about the server has changed. If it was a primary or secondary, it still is. So in this case, the driver does not change the state of the server in its internal data structures. It just throws the exception. Now, when I say that the driver is updating its state, what state am I talking about? So the data structures that drivers use to represent what they know about servers is described in the Server Discovery and Monitoring spec. I wrote this spec about 2 years ago, and all of the official MongoDB drivers have now implemented it. And the spec describes how drivers discover which servers are in your topology, what kinds they are they primaries, secondaries, standalone, MongoS, arbiters, and how drivers keep this information up to date as circumstances change. You may also sometimes hear this spec referred to as SDAM, but I discourage the use of that acronym. When we're talking to each other, we should use the full name so we know what we're referring to, but if you hear that acronym, at least you know that it's the Server Discovery and Monitoring spec. So the spec says that drivers record the type of each server that they check. So if you're connected to a 3-node set with a primary, the driver's internal data structure might say that server 1 is a primary and the other 2 are secondaries. And if there's a network blip, the spec says that the driver should mark the server unknown instead. So now it doesn't know who the primary is anymore, and then it throws an exception. After that, if you try another operation, then the driver will recheck each server twice per second for up to 30 seconds until either the primary is discovered again or we reach the timeout. In the case of a network blip, nothing actually happened to the server, it's just that the socket was broken. So about half a second later, the driver will check the primary again, rediscover that it's a primary, and continue as normally. The original operation we attempted is canceled, but the next operation is sent to the primary normally as soon as it's discovered. In the case of a failover, on the other hand, after that not master error is detected, we act the same, we mark the server unknown, and we start checking each server twice per second. But then, let's say that the former primary comes back as a secondary, and now we have no primary, so we'll keep checking and checking, and then a second or so later, the election completes and a new primary is discovered. These days, MongoDB elections only take a second or two, and the driver will discover the outcome of the election about half a second after that. Again, the first operation, the one that discovered the failover, is canceled, but the next operation blocks until the new primary is found, and then the new primary is used for the operation. If you want to know more about the Server Discovery and Monitoring spec, check out my talk from last year from MongoDB World 2015 called MongoDB Drivers and High Availability, a Deep Dive. There I talk in great detail about the language and the data structures described in the spec and how the spec tells drivers how to respond to these sorts of errors. So that's a great background for this talk about resilient applications. So now that we understand how drivers work, how do we make this update one operation happen exactly once in the face of everything that might go wrong? So I've seen a lot of bad retry strategies. Kind of the default is to not retry at all. And this strategy fails in 2 of the 4 error cases. In the case of a network blip, you try to send the message to the server and you don't know whether the server receives it or not. All you know is you can't read the response. So in the face of a network blip, if the server didn't receive the original message, then we will undercount because we'll throw an exception, we won't retry, and we'll just log the error or whatever and move on. Maybe show an HTTP 500 page to our application user. In the case of a primary failover, we definitely undercount because the server we thought was a primary returns a not master error. It does not process the update message, and we don't send it to the current primary. Interestingly, in the case of a long-term network outage or a command error, not retrying is actually the correct strategy because a network outage, by definition, is something that's not going to end soon, and a command error, similarly, probably isn't transient. If the server is out of disk space or we're not authorized to update that document, trying again is a waste of time. So don't retry is correct in half of the circumstances. A lot of people try to improve on this by just retrying 5 times, or maybe if they really care about their data, they'll retry 10 times or 20 times. I've actually seen this in a number of production applications. There's an engineer named Sam from Rackspace. I talked to him on the phone last year because he'd inherited some code that had this bad retry strategy where it just tried over and over and over again whenever it received any kind of exception. And Sam was wise enough to see that this was a pretty dumb idea, to be frank. But like Ian, Sam wanted to know if we'd published anything that gave him a single smart retry strategy that would allow him to make his application resilient. And he saw that we didn't really have anything, and he wanted to talk to me about, he'd seen PyMongo was re-implemented in terms of the server discovery and monitoring spec. He suspected that there was a better retry strategy out there, but he just didn't know what it was. And it was out of that conversation with Sam from Rackspace that I realized that I could now create this smart strategy and write this talk. So what did Sam see? What's wrong with this blunt retry strategy? So in the case of a network blip, we no longer risk undercounting, but now we risk overcounting. Because what if that first attempt actually succeeded, even though we couldn't read the response? Trying again and sending that same message to the server again will cause us to increment the counter twice. In the case of a primary failover, this strategy actually works quite well because the former primary definitely rejects the update, and then the next time we retry it, we'll re-enter the driver code, which will block checking every server twice per second until the election completes, and then that operation will be sent to the new primary. So in the case of a primary failover, we actually execute the update exactly once. So that's the only correct case for the retry. Retrying 5 times, though, is a waste of code. One retry will succeed. In network outage, on the other hand, retrying more than once is just a waste of time. After that first attempt had failed and the retry fails, we've now spent 30 seconds within the driver retrying every server, rechecking every server twice per second. After that, trying again, re-entering the driver's own retry logic is just a waste of time. We should only try once. And the same with a command error. If we're not authorized, then retrying 5 times isn't going to change that. So it's a big waste of time, and it will cause queuing and latency in your application for no good reason. So I've mentioned a few times that retrying only once will take advantage of the logic that the server discovery and monitoring spec describes in all of the drivers. So maybe we should do that, but only if we get network errors or failovers, not for command errors, which we know are not transient. So let's see how that performs. If we retry once except for command errors, we've still got the problem with network blips where if the first message was processed but we couldn't read the response, then the second message will cause an overcount. But for the same reasons as before, the first retry will succeed if there's a primary failover, and only retrying once, that works well if there's a network outage, right? The first attempt gives us an error from the network layer, and so we don't know if we're dealing with a blip or a long-term outage. If the retry also fails, then we're in an outage, and we should cancel the operation and throw an exception. And in the case of command errors now, our strategy is not to retry them at all, and again, because they're probably not transient, that's the correct strategy. So we've only got one red square left. How are we going to get over this final hurdle? how are we going to avoid the possibility of overcounts? The answer to that is to make all operations idempotent. Idempotent operations are ones which doing them twice has the same outcome as doing them once. You can safely retry them without any danger of overcounting or any other kind of incorrect data that results from replaying the operation. So if we can make all of our operations idempotent, then we are correct in the face of all four kinds of errors because we cannot risk overcounting. Even if we do that update twice, we'll have the same outcome as doing it once because that's the definition of idempotent. But how do we make all operations idempotent? So MongoDB, it has four kinds of operations. There's find, insert, delete, and update. And find and insert and delete are pretty easy to make idempotent, so we'll deal with those first. And only once we've looked at those are we going to deal with update because it's the hard one. So let's look at find first. Queries are naturally idempotent. If you retrieve a document twice, it's just as good as retrieving it once. And insert, it's a little bit harder, but it's not that bad. The first step is that first line there in this sort of pseudo Python that I've written. You generate a unique ID on the client side, and MongoDB's object IDs are designed for this purpose. Once you've done that, you try to insert the document. And if that fails with a network error, then you try it again. If that second attempt fails with a duplicate key error from the server, then we know that the first try actually succeeded. We were just unable to read the server response because of the exception from the network layer. If anything else goes wrong, then we cancel the operation and throw an exception. So this is idempotent. The only warning here is that we're assuming that there's no unique index on the collection except for the _ID index that MongoDB automatically generates for you. If there are other unique indexes, then we actually need to parse the duplicate key error exception to ensure that it was on the _ID and not some other field. If it was on some other field, then we probably have a bug in our application, and we need to deal with that. But other than that, this is a pretty straightforward way to make inserts idempotent. The next one is going to be deletes. If you're deleting one document using your unique value for the key, then doing it twice is just the same as doing it once. If the first one is executed but throws a network exception and we try again, then the second delete one will be a no-op. It just won't match any documents. So we can safely retry this. And delete many is even easier. If we delete all the documents that match a filter and we get a network error, then we can safely try again because deleting them all, again, is a no-op if the first one succeeded. So what about updates? Let's kind of ease into this. We're going to first show the kind of update that is naturally safe to retry, a naturally idempotent update one. This is not the same as the one that we originally looked at in our initial example. In this case, we're not incrementing a counter. Instead, we're just saying that today was sunny. We're setting the sunny field's value to true. And if we say that today is sunny twice, it's just as good as saying that it was sunny once. So in this case, it's safe to retry it. And the general principle here is that there are some MongoDB update operators that are idempotent and some that aren't. $set is idempotent because if you set something to the same value twice, it makes no difference. Whereas $inc, which was our original example, is not idempotent because incrementing something twice adds 2 to it. But if your update operators are idempotent, then you can retry them very easily. You just try once, and if you get a network exception, you just try again. Simple. So now we're finally ready to attack the hardest example, which is our original update one, which is not idempotent. If you do this twice, you'll increment the counter by 2. How do we make this into an idempotent operation? We're going to do it by splitting it into 2 steps. And each of these steps will be idempotent, and by doing 2 idempotent steps, we'll transform this single operation into an idempotent one, which can be retried. The first part of this will be to take the document. So the original state of the document like this at rest, it's got its underscore ID of today, today's date, and the counter value is n. And the first thing we're going to do, we'll leave n alone. We'll just add a unique token to an array, and we'll call that array pending. We need something unique to go here, and an object ID will do great for that. Now the second step is going to be, in a single operation, we're going to delete that token from the pending array, and we're going to increment the counter. It's a characteristic of MongoDB's update operations that they're atomic. If you're doing a single update one on a single document, that update operation either completely succeeds or has no effect at all. So if the token is removed from the pending array, then and only then is the counter incremented by 1. And the final state of the document will be this, where the pending array is empty again and the counter has been incremented by exactly 1. So now we're ready to look at some code. The first step is going to be, we're going to generate that unique token. We'll find the document by its ID, and we'll use $add to set to add that token to the pending array. And $add to set is one of the idempotent operators. If you try to add something to an array that already is there, $add to set won't do anything. So it's safe to retry this, and after doing this once or twice, that token will be in the pending array once. So now we've got the document with the pending ID. What do we do next? So this is a little more code than we've seen before. We can look at it one piece at a time. The first part we're going to look at is the filter. We're updating documents with today's date for the ID that have that token in the pending array. And if we find such a document, then we're going to do 2 things to it. We're going to pull the token out, and we're going to increment the counter. And this operation taken as a whole is idempotent, because if we manage to pull the token out of the array and increment the counter, but then we can't read the server response, and then we try this again, the second time we attempt to do it will be a no-op, because this filter expression here, it's looking for a document with that ID in the pending array, but we've already pulled it out. So the second retry is safe. If the first one actually executed, then the second one will be a no-op. It won't match any document, and so it won't increment the counter. So this is safe to retry. So now we've done it. We've taken that initial update one that was not safe to retry, and we've made it idempotent by splitting it into 2 steps. There's a few caveats to this technique. One of them is that we've turned a simple increment operation into 2 round trips on the network. So we've doubled the latency and we've doubled the load. If you're counting something where it's okay to undercount or overcount once in a blue moon when somebody trips over a network cable, I wouldn't use this technique. So if you're counting page views, for example, and it might be okay to be off by 1 every once in a while, then this isn't worth the extra load and the extra latency. The other caveat is that what happens if we try this second step and we can't do it at all. There's a long-lasting network outage, say, and we never manage to pull that pending ID out and increment the counter. For that, we'll need some sort of nightly cleanup task. It's going to wait until this day is over. So there are no more threads that are updating the document with today's date for their ID. And so there's no more concurrency problems. And so a single thread should run at night and find any pending tokens that are still left over from aborted tasks and updates the counter from them. So that would look like this. You'd use the aggregation framework, and the pipeline would match documents where there are pending IDs. And what it will do is, in that project section, it will add their current counter value to the number of tokens in the pending array. Now, this will return a bunch of results of like truly correct counter values. And what we're going to do is we're going to loop over them. For each document in the aggregation results, we're going to update it, and we're going to set the counter to the sum of the original counter and the length of the pending array. And we're going to clear the pending array by unsetting it. Now, since this is an idempotent operation, right, because we're setting the counter to a value and we're unsetting the pending array, this is safely retriable, and we can keep trying it until it succeeds, no matter how flaky our network is. So as long as we run this background process for the night after we're done trying to count events, then our count of the events for today will be eventually consistent. So if those two caveats are okay by you, that it requires 2 round trips and you might require a nightly job to fix up failed tasks, then for very high value operations, this can guarantee that you will succeed at doing them exactly once. So we finally have an answer for Ian. We have a smart strategy that he can apply over his application. It's going to be resilient and simple and powerful. But maybe Ian's actually not that happy yet, because how is he going to test that he's actually implemented this correctly throughout his applications? For this, I've come up with a technique that I call black pipe testing. So a lot of us, we test our applications as black boxes, meaning we give them some input and out pops the result. But this doesn't give us enough power to cause network outages, timeouts, failovers, command failures. We can't reliably and precisely cause these kinds of errors using a real server as the backend when we're testing our code. So I've come up with an idea that's more powerful than black box testing, and I'm calling it black pipe testing. With black pipe testing, you simulate the server, and by controlling this simulated server, you're able to cause exactly the sorts of error conditions that you want to test precisely and reproducibly. So if you follow this link, bit.ly/resilientapplications, you'll find a link out to a series of articles and a whole bunch of code that I've published that will guide you through the black pipe testing process. It will allow you to test whether you've implemented the strategy correctly. It also links you to articles that I've written about the server discovery and monitoring spec, and if you want a really heavyweight method for very complex kinds of operations, then there's actually instructions there for implementing a 2-phase commit pattern on top of MongoDB, should you need it. The conclusion that I really want you to take away from this is that there is a smart strategy for writing a resilient MongoDB application. It's powerful and effective and efficient and a lot simpler than you might have feared. Thank you very much.